Good evening, everyone. So, my name is Mansi Tripathi. I am a research scholar at IIT Madras. I am TA for the course Environmental Chemistry. So, this is week 6 of the problem solving session. So, first of all, welcome to the halfway to the course. Okay, so in week 6, what we have studied mostly is about the buffer intensity. We have studied about good and bad buffer, like what is good buffer, or what is good quality of buffer we can consider, is where a little more acid or base is required to create some change in the pH. Okay, so it will take some time to adjust. And what is poor quality buffer? Even if you add one drop of any acid or base, there will be a sudden jump in the pH range. So that is bad buffer. So all type of acid and bases have some pH ranges in which it is acting as a good buffer or the bad buffer. This we have seen in the very first lecture of week 6. After that, we studied about buffer intensity. Okay, and all these things we studied by using visual Mintek. Further, we studied about alkalinity and all. So there were many subtopics under these topics, and we studied about acidity as well. So this is the problem solving session regarding all those concepts, so that you can brush up your concepts of the week 6 as well as you can prepare for the examination as well. So the question number 1 is, a solution is titrated using NaOH, sodium hydroxide, which is a base, and the change in pH is plotted against the volume of NaOH. Okay, so as you can see, I'll change the Poitron type. So as you can see that volume of NaOH is plotted against the pH change. So as you have seen in visual Mintek, we were taking very high volume, okay, around 10,000 milliliters. So why we were doing that? So that whatever the volume of titrant you add, in this case NaOH, so it won't change the volume that much. So the error in the volume will be less. So that's why we were taking these things. So this graph is made by using visual Mintek only. So that's why I'm telling you this thing, that the change in volume won't affect much. Otherwise, when we take 10 ml or 20 ml of volume, so there will be an effect due to the volume that is there in your conical flask at present. So this is just the extra information. So question is, which of the pH points have good buffering capacity? So we are talking about good buffers here. So what I have told, what are good buffers? Good buffers are those in which whatever the volume of NaOH or any acid we add, the change in pH is less. So those are the good buffers. So here we have different pHs like 4, 6, 8, 10 and 12. So I want you to let me know what is the pH in which this particular solvent or this particular uh, dilution is showing a good pH, a good buffering capacity. So please have a look at the options and let me know what is the correct answer. So the correct option is pH 4, 8 and 12. Why? You can see, uh, yes, you can see at in the range of pH from here to here, we can see that we need to add 20 ml of sample of NaOH, then only we are getting some pH change, right? And the middle point at point 4, almost sample is there, but the pH change is almost negligible. So that is why pH 4 is the correct answer. Coming to pH 8, in this range, we can see from here to this point. Here also, volume of titrant required is around 20 ml to bring about this pH change. So this is also a good buffering pH range. And the middle average value is 8. Same is happening here. Okay, you can see for pH 12, this line, you can see we added 10 ml, but the pH change is like maybe from 12 to 12.1, okay, or 12.2, and we added 10 ml. So this is also a very good buffering range. So that is why answer is 4, 8 and 12. So these are the pH values where the solution is acting as a good buffer, and where it is acting as a bad buffer, I'll change the color. Yeah. So where is it acting as a bad buffer? This area and this area. As you can see, when we are adding, you can see this area, when we are adding 1 ml or maybe, you can, okay, we'll see the broader area for the better context. When we are adding 10 ml, the pH is changing kind of 1 or more than 1 unit. So these areas are bad buffer. So what we have to see is basically the slope. So if the slope is less, it is good buffer, and if the slope is high, it is bad buffer. So coming to the next question. Two solutions, solution 1 and solution 2 are titrated by adding acid or base in the solution. And the change in pH is plotted against the volume of acid or base added. So like previous question, we are seeing this thing. Which of the following option are true? So various regions are marked in the graph. One is solution 1 and other is solution 2. So first of all, we have to know which solution is representing titration by acid and which solution is representing titration by base. Okay, then you can answer the following question. That at pH above 10, solution 1 is good buffer than solution 2. Option B is solution 1 has good buffering capacity in region 1. Solution 1 has good buffering capacity in region 2, and option D is solution 1 has good buffering capacity in region 3. So we are talking about first this thing. So what I have told is whenever there is a good slope, okay, means a smaller slope, then that solution is acting as a buffer in that particular pH range. So please have a look at the graph properly and let me know what is the correct answer. So the correct answer is option A, B and D. So we'll look at each options carefully. So at pH above 10, so we are talking about pH above 10. Okay, we'll go to this area. Solution 1 is a good buffer than solution 2. Okay, so as you can see, we are going to pH above 10. So we are above this thing. So as you can see here, the change in graph is at the longer run, means from 10 to 12, it is taking, solution 1 is taking this much amount of acid or base. Okay, but solution 2 is taking for that 2 unit change this much amount. So which is taking more amount? That is solution 1. So that's why A is correct option. At that pH 1, solution 1 is good buffer because it is taking more amount of acid or base to get some change in its pH. Option B is solution 1 has good buffering capacity in region 1. So the solution 1 is divided into 3 pH range, region 1, region 2 and region 3. So as we can see, solution 1 has good buffering capacity in region 1 because the slope is less. That's what I have told you. Now talking about region 2, here you can see the change is very sharp. Okay, so here there is no buffer capacity at all. Okay, so the buffering sorry. So the buffering capacity is very poor in region 2. So that's why option C is wrong. Coming to option D, solution 1 has good buffering capacity in region 3. So of course, region 3 we are seeing very good buffering capacity because it is taking longer or longer in this graph, and equivalent more amount of acid or base to bring this much change in the pH. So now the question arises, which is not here. Solution 1, I am titrating with acid or with base. Okay, and what about solution 2? I am titrating it with acid or base. So answer will be very simple. For solution 1, we are saying as the amount is increasing, pH is reducing, right? So solution 1, I'll change the color. So solution 1 is titrated by acid. Okay, because as the amount of acid or base is increasing, the pH is decreasing. So obviously, it has been titrated by acid. Now coming to solution 2, as the amount of acid or base is increasing, the pH is increasing. So obviously, it is being titrated with base. Sorry for bad handwriting. I don't have my iPad right now. Okay. So this is what you should understand from a question. Try to extract as much information as you can extract from a particular question. This will broaden your scope to understand many other similar questions. Okay, so this will be the approach in our question solving. Okay. So this is written, whatever I have told you. Only this thing is written here. Sorry. Okay. So if the change in pH is very less when acid or bases is added to the system, then the system has good buffering capacity in that region. Okay. As the pH change is very less in region 1 and region 3 for solution 1, thus these regions have higher buffering capacity, and as the change in pH is sharp for region 2, we have seen, right, for region 2 change is very sharp, this region. So region 2 has low buffering capacity or poor buffering capacity. This brings us to the next question. A buffer intensity versus pH graph is drawn for multiprotic acid. Multiprotic acid means there are multiple protons or H plus ions, the ions that can be donated at different pH range, at different pH. So if there is a salt or there is an acid having multiple protons, so at different pH range it will have different acidity or basicity. So that is defined by pKa1 or pKa2 values. Okay. So it is, the question is written, it is for multiprotic acid. So these are the various options. By looking at these, you have to tell which of the following option is correct. The graph is for diprotic acid or it is for triphosphotic acid. What about the pKa2 values? pKa2 means one H is already donated. Okay, we are talking about the donation of the second H. Number of high buffer intensity regions are 3 except for the extreme pH values. Okay. Number of high buffer regions are 2 except for extreme pH values. So we are talking about high buffer regions. Please look at the graph properly. Okay, then you can come up with the answer. You can pause the video for now and you can come up with the answer, but think clearly. Okay, how many hydrogen it is donating and where are the regions where the donation by hydrogen is visible, and where are the regions where we can see that there is buffer capacity, high buffer capacity or low buffer capacity, and what are the pH values at that position. So we'll move forward. The answer is graph is for triphosphotic acid. We'll see how. pKa2 is 6.7 and the number of high buffer intensity regions are 3. So there are 3 points pH 3.2, 6.7 and 11 in the graph where buffering capacity is high. Okay, so 3.2, 6.7 and 11. So yeah, we can see here 3.2, 6.7 and 11. So what are the, so we are talking about these peaks. So these are the regions, because this graph is not concentration, okay? This graph is buffer intensity, okay? And we can see these are the regions where buffer intensity is very high, means there are very good buffer at these pHs. That's why buffer intensity is very high. And as you can see, there are three peaks. So this graph is triprotic because we can see there are three peaks. And yeah, it's written over here also. There are three different values of pKa. So thus the graph is for triprotic acid. And what is pKa2? 6.7. Of course, second value will be pKa2. So number of high buffer intensity regions are 3 except for extreme pH values. So what are the position of high buffer intensity? Where pH is equal to pKa. So those are the regions where the buffer intensity was very high. In this question also, where pH is equal to pKa, we will get high buffer intensity. So pKa will be around 10, around 11 here, or second pKa can be around zero point 0.1, okay, 1. So, but this is not very much clear from these graphs. For that, we need to point out, or we need to draw a buffer intensity versus pH graph to get the reason of pKa, pKa1, pKa2, or pKa3, and so on values. So, we are seeing three peaks. That's why it is triprotic. This is pKa1, 1. This is pKa2, and this is pKa3. Okay, so on the, what about the F point? We can see, what about the E point? We can see there are three high buffer regions are three, 1, 2, 3, except for extreme pH values. Okay. So next question is, if H plus is 1 millimolar, OH is 0.01 millimolar, and bicarbonate is 0.1 molar, and this carbonate ion is 0.1 milliequivalent per liter. Okay, please have a look at the unit very properly. Then what is the alkalinity? Please take some time to understand the question. We have H plus, we have OH minus, we have HCO3 negative, which will give H plus, okay. We have HCO3 2 negative, which can take H plus. So we have to consider all these possibilities, and we have to come up with the alkalinity of the solution. And please remember, alkalinity can be negative. Okay, so by looking at this question, it does not mean that option A and B can be ruled out. Alkalinity can be negative. So please try to find the answer of this question. You can use Visual Mintech for this, and you can use basic calculation. Okay, we'll move to the solution. Yes, as I've told, alkalinity can be negative. So alkalinity is minus 0.799 milliequivalent per liter. So I will see how is that calculated. So we have to see the theoretical definition. What is the alkalinity? Alkalinity is equal to concentration of OH bicarbonate 2 times of carbonate minus H plus. Okay, why 2 times? we are multiplying it by their stoichiometric coefficient. So 2 negative, that's why 2 times, and sir has explained very properly how we came up with this equation. So please have a look at that equation. You remember on the left side it was 1 by 2, so it came to right side and it was multiplied by 2. Please have a look at the lecture once again if you want to know how we are getting this 2 CO3 2 negative. And all of these things are in molar concentration. Thus alkalinity is what? 0.011, okay, plus zero point 0.1, yeah, molar concentration, 2 into 0.1, okay, and minus 1. Because it was in milliequivalents per liter, so that's why we converted it to molar concentration by dividing it by 2. Okay, that's why we are getting 2 here. Please have a look at the unit properly. Please ensure that everything is in the same unit. Then only you should go for solving such questions. And this is the answer we got. Hence, alkalinity can be negative. Let's move towards next question. If CO2 gas is bubbled into the solution, then which of the following options are true? We are bubbling the CO2 gas. So alkalinity increases, decreases, or remains constant, and the same things about pH. If it will increase, decrease, or remain constant. You can pause the video, try to understand what does this CO2 gas will do in the water body. So the option C is alkalinity remains constant and pH decreases. So first of all, pH will decrease, that is true. When this CO2 is dissolved in water, it may form carbonic acid and the pH can decrease. This is what's happening in our surrounding also for some lake water body or the river. Sometimes we will see less pH because of this CO2 gas only. Sorry. So, what is alkalinity? OH negative, bicarbonate, 2 times carbonate minus H plus. So, if we will bubble CO2 gas into the solution, H2CO3 increases and it dissociates into H plus and bicarbonate. So, this is the equation how that will function. CO2 is dissociating, when CO2 is getting dissolved in water body, so carbonic acid concentration will increase, and if we know the amount of CO2 in gas phase, how much we are putting inside the water, then we can very well know the amount of carbonic acid. How? By using the Henry's law. Okay, we have studied it, right? Now how this H2CO3 will dissociate? It will give H plus and CO3 2 negative. So this is a two-step reaction. We have written it in the form of one reaction. So because CO2 is dissolving, H2CO3 is increasing, right? So when the H2CO3 is increasing 1 equivalent per liter, then the increase in H plus is 2, but the increase in CO3 is 1. Okay? Because of, look at the stoichiometric coefficient. Increase in, when we are putting it as 1, then H is coming 2 and this is coming as 1. Okay? Now when we will put this inside the formula, OH is same, HCO3 is same. What is happening? 2 times of 1 minus 2 times. So is there any change? 2 minus 2? 0. So that is why the net alkalinity is remaining constant. But as the H plus ions are increasing, because CO2 is being dissolved in this form and it is increasing H plus ions, pH will decrease. Okay? pH will decrease because in pH we are just measuring the H plus ions. We are not considered about how alkalinity is measured. Alkalinity is remaining constant but pH is decreasing. Anyway, there is the reason we call it carbonic acid, right? Okay. We'll move towards next question. And kind of same question. If CO2 gas is bubbled in the solution such that H2CO3 increases by 1 equivalent, which of the following options are true? Total alkalinity increases, total alkalinity increases by 2, phenolphthalein and alkalinity increases by 1 or 2, or H plus increases by 2. So H2CO3 is 1 equivalent per liter. You can pause the video and try to find out the answer. Okay, we'll see the solution now. So the solution is total alkalinity increases by 2 equivalents per liter and phenolphthalein alkali increases by 1 equivalent per liter. However, H plus increases by 2 equivalent per liter. I think for H plus you know how it is increasing, right? We have seen in the previous question. So these are the equations. Total alkalinity is what? H plus total acidity is what? H plus 2 H2CO3, HCO3 minus OH, right? So if the increase in H2CO3 is 1 equivalent per liter, then according to equation 2, this equation, the increase in H plus is 1 and the increase in HCO3 is 1. And what equation 4 is saying? It is for the total acidity in which rise H2CO3 and H plus is 1 equivalent per liter, which raises the total acidity to 2 equivalent per liter. Sorry, I think here acidity term will be there. I'm sorry for my mistake. Because alkalinity we have seen, right? It won't change. So here, when I'll upload the video, I'll upload the PPT, I'll make this correction. Thus, if the increase in H2CO3 is 1 equivalent per liter, then the increase in total acidity is 2 equivalent per liter, because you can see, right? And same phenolphthalein acidity, if the increase in H2CO3 star is 1 equivalent per liter, then according to equation 3, the increase in H plus is 2 equivalent per liter and the decrease in carbonate is 1 equivalent per liter. Equation 5 is for phenolphthalein acidity, in which decrease in carbonate is 1 equivalent per liter and the rise in H plus is 2 equivalent per liter. Thus, the net rise in phenolphthalein acidity is 1 equivalent per liter. Thus, if the increase in H2CO3 is 1 equivalent per liter, then the increase in phenolphthalein acidity is 1 equivalent per liter. Okay, we'll move towards next question. Carbonic acid is given as 0.1 molar. This is a visual Mintek question and the solution is closed, means no CO2 is being dissolved. The alkalinity of the solution after the equilibrium is achieved is, we have to find out the equilibrium, after the equilibrium alkalinity of the solution. Okay. So the answer is 1.487 into 10 raised to power minus 10 equivalent per liter. How we are getting to this answer? We are using equal visual Mintek for that. First, we will put total as 0.2 molar and total carbonate as 0.1 molar. So total H we are putting as 0.2 molar and total carbonate as 0.1 molar. Why 0.2 molar and 0.1 molar? Of course, you know the equation, right? I'll try to write. It's C 2H plus so when we are putting it as 0.1, how much 2 we will get? 2 into 0.1, which is 0.2. And how much carbonate we will get? 0.1. So this is what we are feeding in visual Mintek. You can see here, right? Then we have to just run it and we will get the pH, ionic strength and everything. So number of iterations, how many we are doing? 55. It's a reasonable number. So we will print this in Excel and we will calculate alkalinity according to this formula. We have to do nothing. We have all these values, okay, in concentration. Then we have activity also. So activity and these values are not much different. Then we will just put in this formula and we will get alkalinity as 1.487 into 10 raised to power minus 10 equivalent per liter. Very simple, okay. Coming to next question. Now carbonic acid we are adding as 0.1. Now it is an open system, okay. Last question it was closed system. Now it is open system. It is kept in a room having CO2 gas and H2S gas as well. If the partial pressure of CO2 is this much and the partial pressure of H2S 10 raised to power minus 4, then what is the alkalinity of the solution after the equilibrium is achieved? I told you we will use Henry's law to convert the partial pressure into concentration. And we can solve it easily. Manually also we can solve, but Visual Mintech will make our work way more easier. We'll see the solution. The solution is 6.19 into 10 raised to power minus 10. See, here also closed system. Here our system is closed. Molarity is same 0.1 and there also. But there is a huge difference in the answer. Okay. Here 6.19 and here 1.487. Here alkalinity is coming more. We'll see how. So this equation, this part will be same. Total hydrogen and total carbonate will put same. Then we have to specify the CO2. We will do for each gas separately. First CO2 1 into 10 to power minus 2 atm and then we'll add. For H2S also 10 raised to power minus 4, then we'll click add. Okay, this is how we are adding it. When we can check the added gases. So see, this has converted it into fixed activity, log activity. Okay. Then we will just run the Mintech and we'll get all these values. We will just print them in Excel and we can do this calculation very easily in Excel to get the alkalinity. So just because HS was also there, that's why these two species are increasing in this formula. Otherwise, it would have been ended at H plus ion. Okay, and this is how we get alkalinity. So that was all for today. I hope you liked the lecture. I will upload it and I will upload the PPT as well. I will make that correction that I was talking about. So, okay, have a good day and come for the next lecture. Thank you everyone. Thank you for your patient hearing.